Yeah.
Sorry, I don't think this one is
Yeah, it's okay. Well, I will begin. I guess we can just meet tomorrow and do 5 hours of this course. Since nothing else is happening here, apparently. No? All right. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, I just thank you for this opportunity we have just to meet and study your creation, and just ask you to be glorified in what we do. And just help me to just have a coherent thought today, Lord. In your name I pray, Lord Jesus. Amen. I also begin with, I've been trying to begin with a verse. I told Benjamin to give me a verse to start a class today, so this is what he got for me. Genesis 1:1. In the beginning, God created the heavens and the earth. So you can't go wrong with that one. It's a golden one this year. So, so this is a course in manifolds, and I suppose differential geometry. I'll kind of tack that on here. I would like to talk some about differential geometry. And so manifolds in and of itself, I don't know, I guess there's probably some different people mean different things by these words. Just like you talk about a course in real analysis, what are you talking about? Is it a course in advanced calculus? Is it a course in multivariate analysis? Is it a course about the structure of real numbers? There's a lot of different things that go under that banner. But here just to summarize what we're trying to talk about here, what is a manifold? In a nutshell, a manifold is simply a curved space where you can do calculus. That's it. All right, so our goal essentially is to describe how to do calculus outside the sort of narrow confines of n-dimensional Euclidean space. So I do assume as a prerequisite here that you know how to take derivatives of functions on Euclidean space. So, for example, if you have a function from, say, R3 to R4, how do we calculate the derivative of something like that, right? There's a well-defined procedure. You calculate something called the Jacobian matrix, which is formed from partial derivatives of the function, and you can form the best linear approximation for the function at a point if it's differentiable, right? Alternatively, we could describe that by Fauché derivative and all that. So that's kind of a backdrop. It's good if you've seen those things. If you don't know all that, it actually won't matter that much because it's kind of always in the backdrop, all right? Okay, so let me just get to it. What is a manifold? So definition, a set M is a manifold if it has an atlas A formed by compatible charts. I guess that begs the question, what do I mean by compatible charts? And let's see here. So this is going to be one of those definitions that kind of is unfolding in reverse order because of my poor planning here. But in a nutshell, what's a chart to start with, all right? So a chart, something is going to be, well, we're going to have X, let's say, a mapping from U, a subset of the manifold, to, let's say, Rn, all right? And here, the assumption is that the image X of U is open in Rn, all right? So I guess I do need you to know what that means, all right? And I know you're just starting topology, so maybe you don't. But what that means is that essentially it's got fuzzy edges, all right? So every point in X of U is an interior point. You can find an open ball around every point. It doesn't have any sort of closed solid edges, let's say. So it's an open set. X of U is open. And also this X is a bijection, right? I suppose I should mention In John Lee's book, he doesn't use X, he uses phi for this, right? He says X, basically phi is his notation for X. All right, it's a bijection, its image is open. Let's see, what else can I tell you? So that's just a chart. A chart is simply a bijection from a subset of the manifold to an open set in Rn. That's actually it. All right. Now here we get into something that's a little bit more fussy, which is how are we defining the manifold? There's two different ways to do it. Okay. The one way to define a manifold is to assume a priori before the fact that the manifold is a topological space. It already has a topology which is given. It's Hausdorff. It's second countable, and so if you take that tact, then you also assume that X is a homeomorphism. In other words, that it's continuous with continuous inverse with respect to the topology which is given on M and the topology which is known on Rn, right? But the other way you can define a manifold is just to give an atlas of charts and then to say that that atlas of charts induces a topology, and that's the tact we're going to take in here because we don't know what topology is. So, all right. Now anyway, so let's see here. So some things. I will do my best to give you a poor caricature of what manifold theory is in the lectures here. But if you really want to know, you should read you should read either John Lee's or Jeffrey Lee's book, or both perhaps. So I'm currently kind of dabbling in chapter 1 and 2. Yeah.
Just to make sure, are we really finding a smooth manifold from John Lee, or just
Well, yeah, I haven't gotten to that yet. So admittedly, it's ambiguous what kind of manifold we're talking about, but that's a good question. So to start with, a chart is simply a, yeah.
Oh, are you going to define atlas too?
Yeah, I'm getting there. So a chart is just a bijection from the manifold, and the manifold doesn't have to be an Rn. It could be a set of matrices. It could be a set of equivalence classes of lines. There's all kinds of things it could be. All right. All right. So then, atlas. So what's an atlas? It's a collection of charts. So something like this. You usually use an A, something like and we usually write charts as a pair, something like U alpha X alpha, I suppose, something like that, such that alpha is in lambda, some index set, all right? So it's a collection of charts. And for it to be an atlas, there's some terms and conditions that have to apply here, all right? So one of them is that the union over all the chart domains, it has to give you M. It has to cover the manifold, right? First of all, the charts, the chart domains, the totality of their union, it must cover the whole manifold, all right? That's the first thing. And I think that's essentially where this concept of atlas comes from, right? Like it's like we think of these as sort of maps of the curved space, and if you put them all together, it gives you a map of the world, which is M, which is kind of like what an atlas is, right? An atlas is a collection of maps that describe some geography. So that's the terminology. Now, but that's not it, right? What else is there? So it's a collection of charts. And now I'm going to say compatible. I should really say compatible charts. Sorry, my bad. I'll use one of these deals here. Compatible. And so what's that mean? Well, that means that if you have alpha, beta in your index set such that U alpha intersect U beta is not empty, right? If you have a non-empty intersection of two chart domains, in that context, they have to agree in some sense. Now, they don't have to be equal. That's way too strong, but they do have to be compatible, and that's where we actually start to touch base with Ernesto's question. Is like, is this a smooth manifold? Like, what kind of manifold are you talking about? So the kind of manifold we're going to talk about, it's all covered by the nature of what's called the transition function between the charts, all right? And so at this point, I usually draw a picture. So here is my stupid picture for a manifold. All right, and so let's suppose we have two chart domains that are, I really should probably draw, I should really draw it kind of like a dotted thing. I don't always draw them dotted because it's just tiresome to draw dotted things, but you know, they are open, they are going to be essentially, so you know, for those of you who know topology already, the chart domains form a basis for the topology which we generate. They're your basic open sets, and so essentially arbitrary unions of your basic open sets forms the open sets and the topology which is generated by that basis. And that turns out to be equivalent to the natural basis which would be given in the other viewpoint, assuming that M is a second countable Hausdorff space and that the charts are homeomorphisms. If you take that tact, then it will be the case that the chart domains form a basis for that same topology. You can prove that. I think it's an exercise in John Lee's book. All right. It's probably proved in great detail. John Lee has a number of books, by the way. He has another book which is called Topological Manifolds, which is just about the topology of manifolds. It's just it. You think he's got a lot of details in topology and smooth manifolds? Well, look at the topology of manifolds book. He also has a book on Riemannian manifolds, which is so like if I could take, I don't know. Anyway, let me shut up about that. I made my choice, maybe. The truth of the matter is I'm probably going to jump. But anyway, so suppose you have these two chart domains and they intersect, all right? So you got some point, you got some intersection here, right? Like that. There's some non-trivial intersection. And so the way I picture this, right, and the way we should picture chart domains is essentially, it's a way of laying a grid, right? It's a way of laying a grid, in some sense, on the, on the manifold. So here's my x sub alpha, here's my x sub beta, and those go down in here, Rn, all right? And so, now to be fussy, they actually, the image of u alpha and u beta is some kind of big, let me just kind of draw it like this. I don't know what it is exactly. It doesn't really matter, this is just a schematic picture, right? So there would be like my x sub alpha of u alpha down here, x sub beta of u beta. Those are open subsets of Rn, all right? Well, that's one of the things about a manifold that is not true about an arbitrary topological space, is that it does have to have sort of a uniform dimension. Like you can't have a manifold where you're sometimes two-dimensional and sometimes four-dimensional, sometimes three-dimensional. That won't work. That's not something you can have for a manifold. It is something you could have for something like an orbifold. An orbifold is a manifold with singularities. So there you could have a drop in dimension in places where there's some sort of singular point. Anyway, getting back on track here. So now there's another thing you can do. You can, without loss of generality, you can shift. You can always, like, if there's some point in the intersection we're interested in, P, right, point P in the manifold, you can arrange it so that x sub alpha of P is 0 and x sub beta of P is 0. Like you can shift the point of interest to being at the origin and center your open set around the origin, because you can always shift. You can always translate the image by just adding or subtracting a constant vector. So if the open set was somewhere else away from the origin, you can always move it back here by a simple shift. So a lot of times when you read proofs, you'll see that that's done. All right, don't be bothered by that. Okay, but anyway, now the intersection, though, you see that's smaller, and so that's a smaller. The image of the intersection is something more like this, right? And then the image of that over here is, I don't know what it is, something like that, right? So basically, you got this, you got that, right? And if you want to follow it, we can go from here to here by what map? If I look at you funny, it's just because my eyes are messed up today. Like my left eye, my right eye, they're like not in sync. So I've got like a different like focal, it's like I've got magnification of 100 on one side and like 80 on the other, and it's just messing with me.
Could it be inverse, like x beta
X beta inverse composed with X alpha. Very good, yeah. So that right there, and so like this is, I was just scanning through Jeffrey Lee's book, and this is like one of the things I absolutely love about Jeffrey Lee's writing is he does have a penchant for pedantic comments that are super helpful in places, and he had one about this, which I would have marked ahead of time if I had been more, or I just read it, now I don't know where I read it. But he actually has this like comment somewhere where he's like, so in this context we just write, it's typically written, where is that stupid comment? That's gonna be bothering me if I can't find the stupid thing. Yowzers. This is where my eyes being out of focus is very much not helping. Well, anyway, in there he actually, I mean, I can do it. Let me just do it. Oh, it's on page 11. So he's like, oh, curses. He's got it for the other map though. See, he's looking at this one. What's this one, guys? The other way. Yeah, X alpha. Yeah, X alpha inverse composed with X beta, I believe. Yeah. Wait a minute.
X beta inverse.
Oh. It should be on top. X beta.
Let me just check on this. Oh, see, this is you guys fished me into it. Look, this is not right. Okay. Fun fact: I have a poster once I won second place for, where I have this composition screwed up. No one noticed. It's like that. So, see, the thing is with composition, the last is first, and so we read them right to left, right? So X alpha inverse is the first thing, then you get up here, and then X beta is the second thing. And down here, X beta inverse is the first, and then X alpha is the last, all right? So there we go. Now those are legit. Yep.
But would X...
Whew, glad I looked at Jeffrey Lee's book, yeah.
But would X alpha map U beta? I mean, does it work like that?
Would X alpha...
Or it can...
No, but
Well, so let me just copy down this little, and so here's this is I'm not sure I'm tracking your question, but I think you guys figured out.
that mapping is only for the green area, right?
Yes, that's the remark I'm actually about to make. So X, yes. So here what he says is that X, good, we're on the same page here. X beta composed with X alpha inverse is actually shorthand for what? For X beta restricted to the union of alpha and beta chart domains composed with X sub alpha inverse restricted to X sub alpha of the image of U alpha intersect U beta. Right? So this is actually what's going on up here, right? Like you guys told me, really the X sub alpha inverse, it's only on that green part, right? The green part would be the image under X alpha of that guy, right? And then, well, this green part over here is actually, well, anyway, there it is. So, but anyway, nevertheless, we're just going to write X sub beta composed with X sub alpha inverse and X sub alpha composed with X sub beta inverse, because we don't want to, lose our mind fussing about the domains for the composite. But of course, it should be understood that you do have to restrict the domain in order to make sense of that composition. That's kind of if the U alpha and U beta were just equal, then this would hardly be interesting. All right. The fact that they're not equal is what's interesting. Okay. So that's the setup here. Whenever we have overlap of two chart domains, we need the so-called transition functions, and that's what these are. So like x sub beta composed with x sub alpha inverse, and x sub alpha composed with x sub beta inverse. These are transition functions. Really, they're describing the change in coordinates, right? They're change of coordinate maps. Or you could say they describe the change in coordinates. They describe the change of coordinates. See, x alpha and x beta are two different choices of coordinate at that point P, right? And, okay, so I still haven't told you what's the condition, right? Well, here's the deal. Whatever condition you put on the transition functions, that tells you what kind of manifold you're dealing with. If there's no condition, if it's just essentially, that these have to be continuous bijections, all right? Then you just have what's called a topological manifold. So a topological manifold would be, you just strip it down to its bare essentials, these have to be continuous maps, all right? If you have a so-called C1 manifold, then the transition functions would be once differentiable. You have a C2 manifold, the transition functions are twice differentiable. A C3 manifold, 3 times differentiable. A smooth manifold means that you can take derivatives of arbitrary order of the transition functions. So that's going to be our assumption. We're going to assume that these are smooth. So that makes Rm a so-called C infinity manifold. C infinity manifold. There's apparently a result of Hassler-Whitney. Whitney is he did some very deep work in manifold theory. And just to tell you what happened there, what Whitney showed is that ultimately any manifold, you can actually view it as a subset of Rn. Once you get a little bit further into the discussion, that makes sense. Like yes, we're setting up everything abstractly, but at the end of the day, we can actually view M as a subset of Rn. And this is essentially what Whitney proved. But another thing Hassler-Whitney proved is that if you have a CK manifold, all right, and if you have, well, more specifically, if you have a CK function, a set of like k times differentiable functions, inside that set, there is a subset which is smooth. So if we were dealing with a k times differential manifold, we could still we could still limit the discussion to a smooth manifold inside that context. So maybe there's not as much difference between the smooth and the CK manifold as it first appears. I don't know how powerful that comment is, but that's something I just read in Jeffrey Lee's book. So he's got a lot of tidbits like that of like pretty deep theorems embedded in the chapter. I think it's, anyway, I'll stop trying to sell Jeffrey Lee's book. Any questions so far? No? Okay, so, all right, let's see what else let's do. When I took manifold theory, it was the second course I had of this kind of stuff. The course I had before this course was a course in elementary differential geometry. And elementary differential geometry concerns really just the differential geometry of surfaces and perhaps curves. And there, we also look at what's called a patch, all right? And so I will use this terminology from time to time. A patch, or a parameterization, if you will, of a manifold is just the inverse of a chart, all right? So like, I would say that, x alpha inverse and x beta inverse, these are examples of patches. So a patch is, or a parameterization, this you saw in Calculus 3. Like this is how we set up surface integrals. We had a parameterization from R2 up to the curved surface that we were doing integration on. That was that's a parameterization, it's a patch. Like the big R of UV you might have used, or if my course X of UV, right? Well, so sometimes it's convenient to talk about a manifold in terms of patches, but that's one of the things that sort of separates manifold theory, as it's usually presented, from, say, differential geometry, elementary differential geometry, is that we tend to talk about charts rather than patches. Patches are easier because they take their domain in Rn, so it's just kind of less abstract in a sense, but I think charts are better because they're really closer to the spirit of what we're trying to do, which is to build calculus on curved space. All right? Okay, let's see here. What else can I tell you? All right. What was it? Oh, this is before your time. Before your time, you guys. But there's like the head of the army back in the Gulf War. He said you go to army with the army you have, not the army you want. You ever hear this quote? You go to war with the army that you have, not the army that you want, or something like this. He may not have been talking about the people. He might have been talking about the. He probably was talking about equipment. It'd be kind of rude to say that about the people, right? It's probably not what he said. What was this? Norman Schwarzkopf, was it? Stormin Norman? I don't know. That was before you guys were born. Let's see here. Okay, so. Just trying to get things in place here. Definition. If we have f from, let's say, u, I don't even want to use u because I'm using u as a chart domain here. Well, whatever, I'll use v instead. There, that makes it totally different, right? Subset of Rm, and let's say, I'll say v1, v2, subset of Rm is smooth. Well, let me dial it back a second here. So I've been using this term smooth as if you know what it is. Let me just take a second to elaborate on that for a minute. C1. Really what I should say, let's say if, then f as an element of C1 on V implies that the Jacobian of f, all right, which by the way looks like this. So it's like partial f, partial, and well, see, this is what I've been debating, and I was hoping to get this out of my system before I started teaching in here, but I apparently have not. It's like, do we want to use a different notation for the coordinates on Rn versus the abstract, like, manifold coordinates, all right? So let me do that. I may regret this, but I'm going to try it for now. So, like, let's say that the coordinates on Rn, the Cartesian coordinates, are u1, and then the next one's like u2, and then the last one un. All right, and you guys know how to take partial derivatives, right? So we fix one of the, we vary one coordinate while fixing the rest of them, all right? And so that's the Jacobian matrix. This is a, this is an m by n matrix of functions, right? So to say that, and I could be more another way to look at this, and this might be helpful if you guys are, you guys have various levels of exposure to advanced calculus, so let me just say this also. You could also look at it as a stack of gradients. All right, so like, and I usually put a transpose on here because I think of the gradient as a column vector, so to make them rows, I need to transpose them. All right, so f has m component functions, all right? And yeah. So it's an m by n matrix of functions, which we can either look at as a bunch of partial derivatives glued together or a stack of gradients stacked on top of each other. And to say that it's C1 means that every one of the functions that's a component of this matrix is continuous. All right. To say, so in other words, this function would be what's called continuously differentiable. All right. And in the advanced calculus course, I delve into that more deeply and look at the relation of that to like the Frechet derivative and how that all works. But that actually doesn't matter too much to this course, so I'm going to leave that for there. If we put, instead of 1 there, if we put a k there, then that simply means that each one of these component functions is k times differentiable. And to say that it's smooth is to say that all of these component functions, all these partial derivatives, are as many times differentiable as you want. Yeah?
Sorry, the C1, is that the one you were talking about?
Yes, yes. So if I put a k here,
Yeah, I was just looking at
then which have k continuous partial derivatives. Right, so that's what we mean by smooth. Just to be, I mean, that gives you something you can work with for problems, all right? So if you're probably the homework and you have to decide whether or not this, manifold is like legit, are the transition functions are smooth, then you're just looking at, you just need to find the transition functions and judge whether or not those expressions are actually have partial derivatives which are defined for the context in which they're given. Simple as that. So we don't actually need all that Frechet derivative stuff for the mechanics of this course, is my point. All right. So, obvious question. There's something else I need to get to here. So, a manifold I still haven't quite done it justice because I said M is a manifold if it has an atlas formed by compatible charts. But that's not entirely honest. Because really, let me just say this, a manifold, the better definition perhaps is manifold is set M paired with a maximal atlas A. All right, what do I mean by maximal atlas? All right, so here's a lemma. And this probably make a good homework problem. I should probably use this for a homework problem for you guys because it's pretty basic. But here's the lemma. If, let's say A1 and A2 are two atlases. I'm not sure that's actually how you spell it. Atlases for M, right? Then the union is an atlas for M. And what do I mean by union? I just mean that you put a few more pages in your book, right? Like your Atlas 1 has all of the charts in it, like all those different pages, and your Atlas 2 has all those other pages, so you just glue them together. Now you've got a book with however many more pages, right? And now that begs a question, right? Which is, wait a minute, how do you know compatibility follows? Right, you see? So parts of this lemma are very easy to prove, right? If the union of all the chart domains in the first one gives you M, and the union of all the chart domains in the second one gives you M, well, if you take all of the chart domains together collectively, you still have a union which is M, right? So covering M is easy, right? The issue is, and if you look at two chart domains that have overlap in the union one, right? And those two chart domains are both from the same atlas, well, then you already have compatibility, that's assumed. But the issue comes, of course, when you take two different chart domains, right, which have an intersection, and yet one is from Atlas 1 and one is from Atlas 2. So how do you prove compatibility? Automatically follows. That's your homework problem. So yeah, there you go. Okay. So, all right, so anyway, it's very hard for me to stop working on a problem that I've set up, but I'm going to resist the urge and I'm going to leave it for you guys, all right? Okay, so if this is the case, right, then what you basically can think about is if you're given an atlas for a chart, I mean for a set, then you can keep adjoining to it additional charts which are compatible, right? And so if you just take the union with all possible compatible charts, this gives you what's called the maximal atlas. There's no larger atlas which contains that atlas because you've already adjoined all of the compatible charts with your given atlas. The cool thing is there's a lot of theorems that if we prove for a atlas, all right, then it implies that that same property is true for the maximal atlas. Just like that's a theorem I'll probably state here at some point. Okay, so a manifold is then is a set paired with a maximal atlas. Another way, now in Jeffrey Lee's book, he says it's a set paired with a equivalence. It's how does he say it? He doesn't focus on the maximal atlas terminology. He says it's a equivalence class of charts, I think. What did he say? I'm trying to find his exact terminology here. Sorry, I should have decided to use this book more than like 2 hours before class, right? It's kind of dumb. All right, I'm getting there. Well, so we're in section 1.3 of Jeffrey Lee's book, if you're wondering, guys. So definition 1.27, he says two CR atlases A1 and A2 on M are said to be equivalent. Oh, my bad. Oopsie. That lemma is going to be hard to prove. It's not true. That's a hard lemma to prove. Yeah. Let's be more careful here. So two atlases A1 and A2 on M are said to be equivalent, provided that their union is also a CR atlas for M. And a CR differentiable structure on M is an equivalence class of CR atlases. A C-infinity differentiable structure will also be called a smooth structure. All right, exercise 1.28. Show that the notion of equivalence of atlases given above defines an equivalence relation. There, that's a better homework problem. It actually makes sense. So, yeah, so this is not true. Let's see here. If provided. Well, I guess what I'm saying, provided A1 union A2 is an atlas, which is kind of a dumb thing to write. So let me erase it. The point is, if you take an atlas and you take the union with all compatible charts, you get what's called a maximal atlas, all right? So if you union two atlases together, the only way that works is if all of the charts which you're unioning are pairwise compatible, wherever there's any kind of intersection. All right. Now, so this begs a question, which is, wait a minute, so you mean for a given set, there could be different manifold structures for a given set, right? So let's see here if I can think of how to say this correctly. Goodness gracious. Yeah.
That first definition, should it say maximal atlas?
No, see, because if you have an atlas, you can extend it to a maximal atlas. So to prove that something's a manifold, it suffices to give an atlas.
The second definition says a maximal atlas.
Yeah, I guess I should say manifold. I'm sorry. Yeah, you're right. You're right. I can't have two definitions, can I? Yeah, I'll get confused about this if I'm not careful. I think the terminology is differential. That's what I need to say. I need to say a manifold. My bad. Thank you, Jeff. That's helpful. So a manifold M paired with a maximal atlas A is called a smooth structure, I think. And I guess maybe I'm still not saying it quite right. I think maybe I should say that the maximal atlas is the smooth structure. Yeah, a C infinity differentiable structure will also be called a smooth structure. And a differentiable structure is an equivalence class of C infinity. So that, yes, the differentiable structure just refers to the maximal atlas. So I really shouldn't even say this. I should say a maximal atlas on A is called the smooth structure. There we go. A maximal atlas A is called a smooth structure. So thank you, Jeff. That was a very helpful question. So then to rephrase my question, for a given set, is there more than one smooth structure?
Has this homework problem already been written?
No, this is like a really subtle question, which leads to active areas of active research. Is in homework question? No. But I should give you an example of, let's see here. All right, so example 1. If I think of M as being the real numbers, all right, and oh, rats. I don't think I can give this example yet. We don't have the technology to understand it. Phooey. We have to talk about what does it mean for a map to be smooth on a manifold, I think, to make sense of this example. So I got to stop. I'm getting the cart before the horse here. My bad. But I'll tell you what it is. If you look at the cube function is clearly like smooth from the reals to the reals. Yet its inverse function is the cube root, which is not differentiable at 0 because it's got a vertical tangent there. So that leads to see, I can't even say it correctly now. I'm going to shut up. I'm going to regret saying this later, so I'm going to stop. But okay, so where are we? So we have a manifold. I've told you guys what smooth means for function. So there are two different directions we can go here. The one is I can tell you how we define smooth for a function from one manifold to another. All right, that's one direction we could go here. But it might be good for me just to give you a couple of examples of manifolds before we go on, right? So let's do that. So what are some good examples of manifolds? So, I mean, I think the most stupid and sort of obvious example of a manifold is just Rn. All right? So Rn is the quintessential n-dimensional manifold. And what's the chart? So you basically just take the chart to be all of Rn. And, I mean, that's the chart domain. What's the chart itself? Well, X is just equal to the identity, right? The identity map on Rn. And that's it. All right. Now, of course, that defines a certain smooth structure, all right? So you take all charts which are, compatible with that, and that would give you a smooth structure on Rn. Example 2, if we take V to be the span of, let's say, V1, V2, Vn over the reals, right? An n-dimensional real vector space, right? In this case, what does a typical point in the vector space look like? Sum I equals 1 to n, right? Of, let's say, x upper I, v lower I, right? We like to use upper I for the coordinates in a manifold. I don't know if I've been doing that up to this point. Oh, that's the first time it's come up. Woohoo! So I don't worry about that so much for these guys because I'm trying to keep it from being weird, but I probably should, for the sake of consistency, put those indices up as well. I'll have to do some soul searching after this class. Anyway, so that's a typical point in the vector space is a unique linear combination, right, of the basis. So, what's the definition of the chart domain here? X of p is equal to, well, x1, x2, right, xn. If you've had my linear algebra, I would just say, well, if this is the basis beta, this is nothing more than like the coordinate representation of p with respect to the beta basis. That is a global coordinate system on the vector space of dimension n. And so, question, like, what about other linear algebra coordinate systems? Like, what if I chose a different basis, like say beta bar? What would the situation be, right? If I had beta bar, v bar 1, v bar n, that's another basis for my vector space. I can define a coordinate system with respect to that as well, right? So like, this would define x bar of p equal to, in my usual notation from linear algebra, like this, right? The coefficients which you need to build a linear combination to build the point, the vector p from a linear combination of the basis vectors v bar 1, v bar 2. How are these coordinate vectors related, right? How are these two things related? Well, they're just related by a matrix multiplication, right? So in this context, if you look at, so if I think of x composed with x bar or x bar composed with x, where should the inverse go? Let's say here, right? These are straight up mappings from Rn to Rn. See, because in this context, all that green funny business doesn't go on. What's the overlap of the chart domains here? Well, the chart domain is all of the vector space, right? So they overlap everywhere. And so the transition functions are actually transition functions on the totality of Rn, right? And if we work this out, the details of this, these are straight up linear transformations. They're linear transformations from Rn to Rn, right? which is to say that the Jacobian matrix is just a constant matrix. It's also the matrix of the linear transformation, which means these are smooth, which means that any two coordinate systems in the sense of linear algebra are compatible. And what we're doing in some sense is a generalization of that, all right? Because the atlas which is compatible with this, this coordinate system I've written out here, it includes many, many things which I have not written, right? Like curved linear coordinate systems, other things for a vector space you don't think about in a linear algebra course. They're all in there. Like, for example, in R3, in the usual smooth structure for R3, we could include properly limited cylindrical coordinates or spherical coordinates. Those would be coordinate systems. They have to be limited because you see the angle degeneracy contradicts our assumption of bijection, right? If we actually let theta circle back to where it started, then we've got a jump, we've got discontinuity in the angle coordinate, which we can't have because our manifold coordinate charts have to be bijections. See, so it's a more nuanced idea than we do in Calc 3. We allow ourselves to have redundant descriptions of certain points because ultimately we're interested in integration, and integration doesn't care if you have something not really defined on like a set of smaller dimension than you're integrating. So like the coordinate defects for cylindrical coordinates or spherical coordinates, they're lower dimensional than 3. They're like, it's either along a plane for like where the angle jump is, or the origin is the worst, right? The spherical and polar angles aren't defined at the origin, right? But do we do integrals with spherical coordinates that go to the origin? All the time, right? It's not a problem. Anyway, something to worry about, I guess. If that keeps you up at night, I guess you might be a mathematician. Or maybe a bad mathematician, I don't know. But okay, so these are 2 examples. Now, but this example is incredibly robust. See, because what is an n-dimensional vector space? Well, what's not an n-dimensional vector space, right? There's so many things that are n-dimensional vector spaces, right? Sets of matrices, n-dimensional vector space, right? So many things. Linear transformations from one finite dimensional space to another, that's a finite dimensional vector space, right? Which you could identify with the matrices which represent it. Okay, so here's another one. So here's like a theorem. If U is a subset of M, then M is manifold, then we can construct an atlas for U as follows. How are we going to do it? Can we make U into a manifold? If U is an open subset of M. Whatever that means, sorry, topology people. So here, U is open. So if U is an open subset of M, you can just, basically take, let's see here. Let's say U intersect U alpha, comma, X sub alpha restricted to U, all right? Such that alpha is in the index set for the manifold and U alpha intersect U is non-empty, all right? So basically take all of the charts which cover at least some part of the open set U and just restrict the domains of the charts to U. Well, that's a manifold. You can easily verify that you still have compatibility. And because the intersection of open sets is open, you still have open chart domains, okay? All that jazz. So, well, okay, well, that's interesting. So you mean to tell me any open subset of a manifold is again a manifold of the same dimension? Well, yeah. And you might think, well, that's kind of boring. Like open sets are kind of boring, right? Like what's the open sets you know about in the real numbers? They're just like open intervals, right? Well, but they're more than that, right? Because the infinite union of open intervals is also open. So if I take the real numbers and like complement out the integers, that's an open set. So something like that is how knots are understood in like 3 dimensions, and knot is a complicated particular kind of shape that people study. The complement of the knots are closed sets, all right? So the complement of those it's got fuzzy edges because the closed edges have been omitted, and the complement of the knot is an open set. And that open set is actually a 3-dimensional manifold. And studying the properties of that 3-dimensional manifold is in part how knot theory is done. So I think it's 3-dimensional. It might be 4. Don't quote me. Not a knot theorist. Oh, hey, that happened. Unintentional. All right, let me go on here. Okay, so let me give you a more specific example of this. So example 3, we can talk about GL, GLN, R. Now, my notation is probably not the book's notation, but I think of this as a subset of R n by n. For me, R n by n is just the set of n by n matrices, all right? This is a n² dimensional manifold. So this is a n² dimensional manifold. Now, up to now, all my manifolds are really boring. They're all flat. They're vector spaces, all right? And that continues to kind of be true for this example. But it's a little bit better because GLN is the set of invertible matrices, all right? And we can actually prove that that's an open subset of the set of all matrices. All right? How is that done? Well, GLN is equal to A in Rn by n such that the determinant of A is not equal to 0. You guys know what the determinant is? I'm not leaving that as an open question. You know what let me make that an imperative. You know what the determinant is, right? You guys know it. So you know what the determinant is. So what is GLN with respect to the determinant? Well, let me put this in a different term. This is the inverse image under the determinant of the set, which is -infinity to 0, union with 0 to infinity. Right? It's the inverse image of that set, right? Those are the non-zero real numbers, right? What's the real number which is 0? Well, it's 0. Everything else is not, right? And how about that? 0 to infinity and -infinity to 0, are these open sets? I'm sorry, you haven't had topology. You don't know what an open set. No, you know what an open set is. You've had real numbers. Some of you have had real analysis, yes? Yes, you know what an open set is. Good grief. So this is the union of two open sets, which is open. And this is the inverse image of the determinant map. What's the determinant map? It is a multinomial in the coefficients of the matrix. In other words, it's polynomial in the components of the matrix. That's a continuous function. Therefore, this is the inverse image under a continuous function, so it's an open set. That's right. So, continuous inverse image of, and this is inverse image of therefore it is open. But it's a n² dimensional open set. All right? Let me show you something a little bit more concrete here. Example 4, let's look at like SL2R. SL2R